the punch force can be determined. Punch force can be determined using this expression. Here, the first term represents the force requirement for ideal deformation. The second term represents the force requirement due to friction and Blank-Waldner pressure. The third expression, third B represents force requirement for bending and straightening of the plank. Notations are given here. Using this expression, punch load can be determined, where P is the total punch load, sigma 0 is the average flow stress, dP is the diameter of the punch, d0 is the blank diameter, capital H is the Blank-Waldner pressure, small h is the wall thickness, mu is the coefficient of friction, d is the force requirement for bending and straightening of the plank. Then we talk about the bottom fracture. Fracture takes place at the bottom of the cup. Punch load is applied to the bottom of the cup. Punch load is transmitted to the side wall of the cup. Usually failure occurs over the punch nose region where bending takes place. The metal is subjected to tensile stress in this region. It is a plane strain deformation. Here both stretching and thinning will take place. If the drawing stress exceeds the tensile strength of the material, bottom fracture will take place. This maximum load can be determined by using this expression. Pmax is given by 2 by root 3 into SU, ultimate tensile strength, into pi into dP. dP is punch diameter into height of the cup. Then we talk about drawability. For a given sheet material, there is a drawability can be measured. Drawability is nothing but ratio of the initial blank diameter to the diameter of the cup drawn from the blank. For a given material, there is a limiting draw ratio, that is maximum diameter that can be drawn successfully. Limiting LDR is the limiting draw ratio, D0 is the blank diameter, P is the diameter of the punch. LDR is given by D0 by dP max. Then we talk about factors affecting the drawability. For example, take die radius. Die radius should be as generous as possible. Die radius should be about 10 times of sheet thickness. Then talk about punch radius. Punch radius should be as generous as possible. Sharp punch radius leads to tearing and thinning. Then we talk about clearance. The clearance between the punch and die should be greater than sheet thickness. It is usually 10 to 40% greater than sheet thickness. Then we talk about hold down pressure. Hold down pressure can be calculated using this expression. That is about roughly 2% of average yield stress plus tensile stress of the material. Then lubricate only die side only. Don't lubricate the punch side. Then we talk about redrawing operation. Redrawing operation is nothing but reducing the cup diameter and increasing the height. Reducing the cup part of the smaller diameter and increasing the height is known as redrawing operation. There are two methods of redrawing operation. One is direct redrawing operation, another one is reverse redrawing operation. Because of direct redrawing operation, the metal is subjected to severe strain hardening. This is due to bending and unbending and the punch and die radii. Then we talk about reverse redrawing operation. Here the cup is turned inside out. So the outside of the drawn cup becomes inside surface of the drawn shell. Bending is always in the same direction. Less strain hardening will take place in this process. You can have better control over wrinkling. Residual stresses are nullified. Increased drawability can be obtained in this case compared to direct redrawing operation. Greater reduction is possible if we go for annealing in between the two draws. Most of the metal permits total reduction of 50 to 80% before annealing operation. Then we talk about methods to improve the drawability. Cup nose wall region must be strengthened. This can be done by using the rubber pads in the tool setter. Drawability can be increased by roughening the punch. Then withhold the lubrication on the punch side, which improves the drawability. Then heat the flange region. So it may shift the failure. That means the better drawability can be obtained. Or by controlling the crystallographic texture, drawability can be improved. Then we talk about texture. Correct texture gives proper orientation of the slip system. So that strength in the thickness direction must be greater than that in the plane of the sheet. Resistance to thickness thinning is measured by plastic strain ratio. That plastic strain ratio R. R is given by width strain by thickness strain. ln of W0 by W divided by ln of T0 by T, where W0 represents the initial width, T0 represents the initial thickness, W represents the width after deformation, T represents the thickness after deformation. Using this expression, R value, plastic strain ratio, can be determined. Then we talk about defects formed in the deep drawn operation. One is bottom fracture, another one is wrinkling, another one is orange fill effect, next one is stretcher strain defect, the last one is earring. This bottom fracture is due to thinning in the punch nose region. It is can be minimized by reducing the thinning by using larger punch radius or decrease the punch load. By decreasing the punch load, drawability can be improved. That is one operation. You provide generous punch radius. When you are giving the generous punch radius, bottom fracture can be reduced. Wrinkling. Wrinkling is due to compressive circumferential hoop stress only. To prevent this defect, you have to apply sufficient hold down pressure to suppress the buckling or wrinkling. Then we talk about orange fill effect. This occurs in the relatively large grain size material. The individual grains tend to deform independently. This can be minimized using the fine grain size sheet metal. Then we talk about stretcher strain defect. It is commonly found in low carbon steel, conventional low carbon steels. This defect shows flame-like pattern of depression on the surface. As the deformation continues, they spread and join together to produce uniform rough surface. The depressions occur along the planes of the maximum shear stress. This is non-uniform deformation which results from yield point elongation. To avoid this problem, you have to give cold reduction of 1 to 2% before annealing operation. During the rolling operation only you have to give 2 to 2% cold reduction after annealing operation. Earring. This is due to formation of baby edge on the top of the drawn cup. This formation is due to anisotropy or directional property of the sheet material. For example, the R value are the mechanical properties along the rolling direction and transverse direction are not same. That's why it is called anisotropy. Earring can be correlated with the planar anisotropy delta R. Delta R is given by R0 plus R90 minus 2R45 divided by 2, where R0 is represent plastic strain ratio along the rolling direction, R90 represent plastic strain ratio value along transverse direction, R45 represent plastic strain ratio value along 45-degree direction to the rolling direction. This plot shows the effect of Blank-Holder pressure on depth of the sheet metal. When the Blank-Holder pressure is low, wall wrinkling will take place. When the Blank-Holder pressure is excessive, bottom fracture will take place. For one particular value or a small range of particular value of Blank-Holder pressure, you will get maximum drawability or maximum height can be obtained. This figure shows the effect of three different drawability of three different grades of steels. This is drawn between the drawability versus Blank-Holder pressure. When the Blank-Holder pressure is very low, wrinkling is a problem. When the Blank-Holder pressure is excessive, bottom fracture will take place. This figure shows how the Tractrix die can be constructed. If you draw a tangent from the Tractrix curve and the punch diameter, it is of constant length. It is of constant length. This figure shows how the Tractrix profile can be obtained. If you draw a tangent from the Tractrix profile to the diameter of the punch, it is of constant length. This figure shows the typical Tractrix die profile. Tractrix die profile. When drawing through Tractrix profile, higher limiting draw ratio can be obtained. That is, drawability can be improved. This is recommended only for thick blanks, thicker blanks. Here, no blank holder pressure can be applied to the sheet metal. This figure shows the typical conical die that can be used for the deep drawing operation. Using the conical die, better drawability can be obtained. Compared to conical die, better drawability can be obtained in the case of Tractrix profile. This figure shows the wrinkled cups. This figure shows the tooling arrangement for the combined cupping and ironing operation. For example, you take Coca-Cola cans and Pepsi cans, two-piece cans. These two-piece Coca-Cola or Pepsi cans can be obtained using this process. Here, the punch is available. Over the die, sheet metal is placed. As the punch advances down, what cup can be drawn. This cup is ironed out in 3 different stages. Finally, deeper cup can be obtained. Two different punch geometries that can be used in the deep drawing process are shown in here. One is flat bottom punch, another one is hemispherical bottom punch. This figure shows the relationship between limiting draw ratio and R average value. R average is R0 plus R90 plus 2R45 divided by 4. This is for different sheet material. This is for removed steel, kilned steel, stainless steel, aluminum, copper and brass. For the case of aluminum, copper, limiting draw ratio is very low. For the case of steel, limiting draw ratio is higher. This figure shows the effect of limiting draw ratio on strain grading exponent n value. As the strain grading exponent n value increases, the limiting draw ratio also increases. As the R bar value increases, limiting draw ratio also increases. This figure shows the relation between limiting draw ratio and R bar value. Here, better correlation is obtained. So, it shows the relationship between L and R, natural logarithm of LDR divided by R bar plus 1 divided by 2. Or another one is natural logarithm of LDR minus 0.14 n square, where n is the strain grading exponent, and R bar plus 1 divided by 2 whole power 0.25.